In today's lecture, we will discuss a very important method. This is known as the Newton's method, and this method will be used for approximating solutions to a given equation. So generally, when we have equations of the sort x squared minus 4 equals to 0, then it's quite easy to solve this equation, and the roots of this equation will be plus or minus 2. However, there will be certain types of equation whose solution will be extremely difficult to obtain. For instance, if we have x multiplied to e raised to the power of x equals to 1, then finding a solution or finding a roots to this particular equation becomes extremely difficult using algebraic techniques. So we'll be resorting to certain types of method, and here the Newton's method becomes extremely helpful. So we'll try to understand in this lecture what the Newton's method is. So let's begin by considering a continuous function f of x. So let's say this is our function f of x. What we're trying to do here is, before beginning with the explanation, we are trying to solve this equation f of x is equals to 0, where f of x is given by this particular continuous curve. So what we will do, we will consider a solution. We will make a guess. Actually, we are trying to make an approximate guess. Let's say the solution to this curve is x naught. However, we are not exactly sure if this is the solution. That is when Newton's method becomes extremely useful. So for our particular guess, we consider the point P, and this point is going to have the coordinate x naught, comma f of x naught. What we will try to do next is we will draw a tangent line which is tangent to this curve at the point P. Then we let the tangent line extend such that it intersects the x-axis at a new point, and we will call it x1. Now from this point, what we'll do, we will draw a vertical line and look for the point where it crosses the curve at the new point. Let's call it P1. So the coordinate of this new point will be x1 comma f of x1. Right. Next, now that we have the new point P1, now we will draw a new tangent line. So this new tangent line is going to pass through this particular point, and this tangent line is going to intersect the x-axis at another point, let's say x2. Again, we are going to repeat the process. So we are going to again draw a vertical line which is going to intersect the curve at the new point P2. We again draw a tangent line, and in this process, the more and more tangent line we have, we will get a better approximation, we'll get a better solution. So what we'll do, first we will begin by considering the first tangent line and find out the slope of this tangent line. So the slope will be given by f prime of x. Actually, x is calculated at that point x naught. So the slope at that particular point P, this will be equals to the change in y value. So that is f of x0 minus, so here the coordinate of this point is x1 comma 0. So f of x0 minus 0 divided by the change in x value, which is x0 minus x1. And now we can rewrite this as x0 minus x1 is equals to f of x0 divided by f prime of x0, or simply x1 will be equals to x0 minus f of x0 divided by f prime of x0. Right. Similarly, if we find out the equation of the second tangent line, so that will be using the same methodology, we will obtain x2 will be equals to x1 minus f of x1 divided by f prime of x1. So if we follow this particular trend, then the general form will be xn plus 1 equals to xn minus f of xn divided by f prime of xn. So this is called the Newton's method, and using this method we can find a very good approximation to our equation. So let's apply this particular formula to finding the solution for some equation. Let's consider this particular equation, x e raised to the power of x is equals to 1. So we want to approximate the root of x e raised to the power of x is equals to 1. So we can rewrite this equation as x equals to e raised to the power of negative x, or x minus e raised to the power of negative x is equals to 0. Now this is our function f of x, which is equals to 0. So that means we'll consider f of x to be equals to x minus e raised to the power of negative x. Now let's take the derivative with respect to x. The derivative of x will be 1 minus derivative of the exponential function is the function itself, but we'll have to use the chain rule to take the derivative of negative x, which will be negative 1. So we get 1 plus e raised to the power of negative x. So this is our f prime of x. Now we'll use our Newton's method, which is given by xn plus 1 is equals to xn minus f of xn divided by f prime of xn. So this is equals to xn minus, so we have f of xn. f of x is given by x minus e raised to the power of negative x. So f of xn will be xn minus e raised to the power of negative xn divided by f prime of xn. So we have f prime of x, so this will be 1 plus e raised to the power of negative xn. Okay, let's combine the two terms. So we have 1 plus e raised to the power of negative xn. So we'll multiply xn with 1 plus e raised to the power of negative xn. So this will be xn plus xn times e raised to the power of negative xn minus xn plus e raised to the power of negative xn. So the first term and the third term cancels out, and this leaves us with xn plus 1 multiplied to e raised to the power of negative xn divided by 1 plus e raised to the power of negative xn. So this is our xn plus 1. So now that we have an expression for xn plus 1, we'll try to find an approximate value to this equation. So if we start with a guess, let's say we'll start with a guess that x0, so this is equals to 1. Let's say if this is a good guess or not. So our equation is x e raised to the power of x is equals to 1. So if we substitute x with 1, then we have e raised to the power of 1 is equals to 1. So this is not a very good guess, because we know that the value of our exponent e is approximately 2.7. So we are actually quite far off from the original value. But then again, to begin with the problem, 1 is a pretty good guess because we are close to 2.7. Also, it will help us solve this particular problem. So let us begin. So we'll use this equation. So our x1 will be, we have x where we have considered n to be 0. So this is x0 plus 1 times e raised to the power of negative x0 divided by 1 plus e raised to the power of negative x0. So we have considered the value of x0 to be equals to 1. So this will be 1 plus 1 times e raised to the power of negative 1 divided by 1 plus e raised to the power of negative 1. So we'll use the calculator, and this is going to give us a value approximately 0.5379. Now this is our x1. So we will use our x1 and then we will find x2. So this time we're considering n to be equals to 1. So x2 will be equals to x1 plus 1 times e raised to the power of negative x1 whole divided by 1 plus e raised to the power of negative x1. So let's substitute the value of x1 with 0.5379, and this should give us approximately 0.5670. Let's take n as equals to 2, and we will have x3 is equals to x2 plus 1 multiplied to e raised to the power of negative x2 divided by 1 plus e raised to the power of negative x2. Now we'll use the value of x2 as 0.5670, and this should give us approximately 0.5671. So we can see that the x2 and x3 values are quite close to each other. So we'll consider x approximate the root of the equation to be 0.567. So let's consider that. So x approximately 0.567 is a solution to x times e raised to the power of x is equals to 1. We can actually verify this. So let's substitute the value of x with 0.567. So with 0.567 multiplied to e raised to the power of 0.567. And this gives us a value approximately 0.9996. And this is quite close to our value 1. So we can say that this is a very close approximation to our solution. So that means using the Newton's method, we have obtained an approximation or approximate root to a given equation. So let's try out another problem. So we'll consider the problem approximate half as the root of 1 over x minus 2 equals to 0. We know that this is a very simple equation. 1 over x minus 2 equals to 0. When we solve for x, it is indeed half. We know for sure that this is the root of this given equation. But what we're trying to do here is use a very simple equation to check out the elegance of the Newton's method and see how close of an approximation it can give us. So let us begin. So we will begin by considering the function f of x equals to 1 over x minus 2. Then let us take the derivative of this particular function with respect to x. So this will be negative 1 over x squared. Now that we have fx and f prime of x, so we can write x of n plus 1, which will be equals to x of n minus we have f of xn divided by f prime of xn, which will be x of n minus, so f prime of xn, we have f of x, this will be 1 over xn minus 2 divided by f prime of xn, which will be negative 1 over xn squared. So we'll have x of n plus 1, so that's equals to xn plus, so we'll take xn squared to the numerator. So this is xn squared multiplied to 1 over xn minus 2, which is equals to xn plus xn minus 2 xn squared, which is simply 2xn minus 2xn squared. This is our xn plus 1. What we'll do next is we will consider a guess. We will consider a root which is very close to our original root. So here we are saying that half is the approximate value, but we are not going to take half, but we're going to take some value which is closer to the original value. So let's say we consider x0 is equals to 0.4. We will use this 0.4, and let's see. So for x naught equals to 0.4 and n equals to 0, we will have x1 is equals to 2x0 minus 2x0 squared. Let's substitute this value. So we have 2 times 0.4 minus 2 times 0.4 squared. So solving this, we should get, so we're getting 0.48. So this is x1. Now we will use x1 to calculate x2. So we have x1 is equals to 0.48. We'll consider n to be 1. So this will give us x2 equals to 2x1 minus 2x1 squared. We have 2 times 0.48 minus 2 times 0.48 squared. So this should give us 0.4992. Next we consider x2 as 0.4992. N equals to 2, which will give us x3, which is 2x2 minus 2x2 squared. And substituting the value of x2 with 0.4992, we should get 0.4999872. We'll do a couple more. So we have x3 equals to this particular value 0.4999872, and consider n is equals to 3. For this we have x4 is equals to 2x3 minus 2x3 squared. So we should give us 0.5. 0.5 is half. So we have shown that this value, this is now a very good approximation, and we have to show that half was indeed the approximate solution to our equation 1 over x minus 2 equals to 0. Problem number 3, we need to approximate the root of x squared minus 10 equals to 0. So let us begin. So first we'll consider the function f of x, which is given by x squared minus 10. Then we find its derivative with respect to x, which will be simply 2x. And now that we have the value, so recursive relationship will be xn plus 1 equals to xn minus, we have f of xn divided by f prime of xn, which will be xn minus, so f of xn will be xn squared minus 10 divided by f prime of xn, which is 2xn. Combining the two terms, so we have 2xn squared minus xn squared plus 10, or simply put xn plus 1, this will be equals to xn squared plus 10 divided by 2xn. So what we'll do, we'll start with a guess. So our guess will be, let's say x0. What could be the value of x such that when we square it, it becomes equals to 10. So we'll take a value x equals to x not equals to 3. Of course, 3 square is 9, so 9 is not equals to 10, but this is a guess. So we'll starting with a guess. Fine. So x1 will be equals to x0 squared plus 10 divided by 2x0. Substitute the value of x0 equals to 3 into this equation. So 3 square will be 9. 9 plus 10 divided by 2 times 3. So this is 6. So we have 19 over 6, and this gives us 3.167. Now we'll go to our second iteration. For our second iteration, we have x2, which is x1 squared plus 10. All we have to do is keep a note of this particular recursive relation. So we have x1 squared plus 10 divided by 2x1. Now in place of x1, we will use 3.167. So this will be 3.167 squared plus 10 divided by 2 times 3.167. So let us plug this value into our calculator, and we should get, we will get 3.1623. Right. Then we'll have x3. So x3 will be x2 squared plus 10 divided by 2x2. So in place of x2, we will use 3.1623, and this should give us 3.1623. So we'll stop here, and we will see if we have gotten a good approximate value or not. So our original equation was x squared minus 10 is equals to 0. So x is simply equals to square root of 10. We're only considering the positive value, and square root of 10, this is approximately 3.16227. So that means we have a very good guess here. We are getting a value. So this is also 3.1623. So our guesswork has been pretty good. So Newton's method is a very powerful method which gives us a very good approximation. That means it's going to be closer and closer to the actual value the more iterations that we take. So see you in the next class.